Next, what we're going to do is we're going to evaluate the Laplace transforms of exponential functions, e to the kt. So this is going to be, just again by the definition, the integral from 0 to infinity, and e to the negative st, e to the kt. We're doing all this with respect to t. Okay, so dt. dt. Okay. In this one, we're just going to take our integrand and write it as a single term. So we get e to the, that's right, that is, I don't need to be too fancy here, e to the negative s t plus kt. So negative, let's just do it that way. So e to the negative s quantity minus k t dt. Okay, because when you distribute, you get when you distribute, you get minus st and then plus kt, right? That's what we did. So this is going to turn out to be, if we integrate this, we're going to end up with negative 1 over s minus k from times 0. So e to the negative s minus kt, evaluated from 0 to infinity. And when t goes to infinity, this goes to 0. And when t is 0, we get negative 1 over s minus k. So this is going to be 1 over s minus k. This only works, by the way, if s minus k is positive. Or in other words, when s is greater than k. Okay, so that's the valid range for that Laplace transform. And this turns out to be a really nice Laplace transform to know, because you can do a lot with exponential functions. So what we're going to do is we're going to use this to find the Laplace transforms of the hyperbolic sine and cosine functions. We'll actually use this to find the Laplace transform of cosine and sine. So we've already seen what that is, but this is just another way to do it. Before we do that, we need to talk about some properties of the Laplace transform. And so the properties of the Laplace transform that are going to be relevant for us are the following. So we know, we've already seen actually, if you have the constant times the function in the Laplace transform, you can bring the constant out. Okay, we've already proved that. But it also turns out that the Laplace transform has the following property, so that if you were to add two functions and take their Laplace transform of that addition, this is going to be the sum of the Laplace transforms. Okay, so Laplace transform of f plus the Laplace transform of g. This follows just by writing out the definition, using properties of integrals, and then recognizing those integrals as Laplace transforms. In fact, this is short enough. Let me just prove this. This is a super easy proof, so why not? So if I look at the Laplace transform of f plus g, this is going to be the integral from 0 to infinity e to the negative st times f plus g. And then based on what we know about integrals, you can distribute the e to the negative st, you get a sum in the integrand, and then you can separate this into two integrals, e to the negative stf dt, plus the integral from 0 to infinity e to the negative st g of t dt. And that's nothing more than the Laplace transform of f plus the Laplace transform of g. Okay, it's always nice to see a proof if necessary, but that's it. So you just write it out, it works, everything is good. This shows you, by the way, for those that have taken linear algebra or are taking it right now with me, this shows that the Laplace transform L is a linear operator. Okay, if you've not taken linear algebra, you can ignore this fact. In fact, even if you are taking linear algebra, you can still ignore this fact. But this is just how I remember all the properties of the Laplace transform. It turns out the Laplace transform is a linear operator, and this is linear in the sense of linear algebra. Okay, so it's linear in the sense of linear algebra. Okay, so linear operators are operators with certain properties. In fact, it's operators with these two properties. But there we go. So Laplace transform operator is linear. All right. With that being said, let's look at a few other Laplace transforms. So let's look at, I want to find 4 more now. So let's look at the Laplace transform of hyperbolic cosine of kt. And if you remember by the definition of hyperbolic cosine of kt, this is going to be, so this is going to be e to the kt plus e to the negative kt all over 2. And so what that is it's going to be, I can just use the facts that we just talked about for the Laplace transform. I can bring the 1/2 out. So this is 1/2 times the quantity e to the kt plus e to the negative kt. So you can bring that 1/2 constant out. You're left with the Laplace transform of e to the kt plus e to the negative kt. And then we can use our second property that we know, that the Laplace transform is additive. So if I have the sum of 2 functions, this will be the sum of the transforms. So to say it, the transform of the sum is the sum of the transforms. Very pithy, right? It's a bumper sticker. And this turns out to be something that we know how to do, right? We saw that if we take the transform of e to the kt, what we end up with is 1 over s minus k. And by extension, if I take the Laplace transform of e to the minus kt, we'll end up with 1 over s minus a negative k. So it's 1 over s plus k. And we can factor out the 1/2. So I'm going to do this all in one step. Combine the fractions, so that'll give us s plus k plus s minus k all over s squared minus k squared. And it turns out that this is going to give us 1/2 of 2s over s squared minus k squared, which is s over s squared minus k squared. And there's another transform that we know. So this is hyperbolic cosine of kt. Okay, it turns out, I'm not going to walk through this whole process again, but it turns out that if you take the Laplace transform of sinh of kt, any guesses what you would end up with? You're probably right. You would end up with k over s squared minus k squared. Okay. And finally, what I want to do is show you how to use these facts, the Laplace transform of the exponential, and put everything together to get the Laplace transform of cosine and sine. And so one of the things that we're going to utilize here, one of the things that we're going to take advantage of is we know that e to the I theta is cosine of theta plus I sine of theta. And so that means the e to the minus I theta is cosine of minus theta plus I sine of minus theta. And that means that, let me just rearrange this just a little bit. So that means that e to the minus I theta is going to be cosine of theta, because cosine is an even function, so you can lose that negative, and then minus I sine theta. Okay, so sine is odd, so that minus comes out of the function. So minus sine of theta. Okay. And then I'm going to look at these two terms together. Okay, so I'm going to look at these two terms. And it turns out if we add them up, if I add up both of these equations, we're going to see that the sine terms cancel, and e to the I theta plus e to the negative I theta is equal to 2 cosine of theta. In other words, cosine of theta can actually be written as a sum of exponentials, e to the I theta plus e to the minus I theta. And if you were to subtract these two terms, you would see that e to the I theta minus e to the negative I theta. Here the cosine terms will go away and you get I sine theta minus a negative I sine theta, which will give you 2I sine theta. So that sine of theta would be equal to e to the I theta minus e to the negative I theta over 2I. From this you can see that sine and cosine behave a lot like hyperbolic cosine and hyperbolic sine. So for example, if you were to look at cosine of minus ix, what you would get, just based on our formula that we have above, is e to the I minus ix plus e to the minus I minus ix all over 2. So this would be I times minus I is 1. So this is e to the x plus e to the negative x over 2. This is nothing more than hyperbolic cosine. Okay, so next what we can do is we can use what we know about exponentials to get the Laplace transform of cosine of theta. So the Laplace transform of cosine of theta is going to be, this is the Laplace transform of e to the I theta plus e to the minus I theta over 2. And this is going to be 1/2 times the Laplace transform of e to the I theta plus 1/2 the Laplace transform of e to the minus I theta. And you can factor out the 1/2 if you'd like. The Laplace transform of e to the I theta, we know how to deal with exponential functions. The Laplace transform there is going to be 1 over s minus I. And likewise over here, it's going to be 1 over s plus I. And when we combine these, what's going to happen is we're going to end up with s plus I plus s minus I over that product, s minus I times s plus I. And so that's going to be 1/2. In the numerator, the i's cancel. We end up with 2s. In the denominator, we're going to have a difference of squares. We're going to have s squared minus I squared. And so the 2's cancel. We end up with s over s squared plus 1, because I squared is minus 1.